Hello, everyone. This is panel 9 with the session called Product Regulation, Becoming Digital, Environmental and System-Oriented. I'm Eva Geilinger and I'm co-leading this panel together with Thomas Goetz. And we have a very interesting session coming up. The presentations and the speakers will give an outlook on what product policy might become in the future and how we can make it even bigger, better, and stronger than it already is. I want to ask the listeners that are now live to post your questions very early during the presentation. So the speakers can make really the best use of this very short 5 minutes that they have afterwards to discuss questions. So first up is Thomas Adesar. Thomas is a research fellow at the Wuppertal Institute for Climate, Environment and Energy in Germany. He will show us what a digital product passport could look like. So let's see his presentation.
Welcome to this presentation, or to the recording of my presentation. Since my partner and I are expecting a baby any minute, I decided to better provide you with a recording of my presentation, just to be on the safe side. Well, maybe another minor remark at the beginning. As you will see, the concept of the digital product passport, which I'm going to present, is only evolving. And if you're interested in investigating the concept any further, please drop me a line so maybe we can set up some research project. Okay, then let's get started with the digital product passport, or in short, DPP. As the DPP is rather an instrument to drive circularity, I decided to start with a bit of an introduction on circular economy aspects. After that, I would like to talk about how the concept of the DPP evolved in recent years. And then I will illustrate an overview of how the DPP may work and how information flows might be organized for an electronic product based on information and ideas available so far. Next, I would like to sketch how information flows are organized for the same electronic product under current legislation before giving a brief comparison of the two. By implementing the digital product passport, one could think of adjusting several initiatives on the EU level for electronics, and I, in fact, would like to focus our attention on EPREL, which is the European product database for energy labeling. And in the end, I would like to get your view on the digital product passport and discuss important steps in order to achieve synergies between a future DPP and the existing legislation for energy-related products. Circular economy is assumed to bring along huge benefits in terms of CO2 savings. It can boost the economy and create jobs. This figure shows that CO2 savings of more than 50% are possible if steel, plastics, aluminum, and cement become circulated in the EU. According to the EU Circular Economy Action Plan, circularity is supposed to be strengthened in the energy and climate plans, which member states have to set up periodically. But also internationally, the EU seeks to advance circular economy through alliance building. And the Circular Economy Action Plan highlights the EIT, the European Institute for Innovation and Technology, to advance innovation action for circularity. Well, here you see a timeline of relevant publications that mention the DPP as a policy tool. On the top level, you can find relevant activities on the EU level. The Green Deal, the aforementioned Circular Economy Action Plan, the draft Council conclusions under the German presidency, and the Sustainable Products Initiative. for which an inception impact assessment was published in September, and its legislative proposal is supposed to be published in the fourth quarter of this year. At the bottom, there are activities initiated in Germany, like the Digital Policy Agenda for the Environment. We have a discussion paper published by the European Policy Center that was assigned by the German Federal Ministry for the Environment. The very same ministry assigned the Wuppertal Institute to write a scoping paper whose results were fed into the German Council presidency, and which also resulted in a research paper on the DPP. Finally, Germany's Federal Environment Agency published a project tender on product information, in which the concept of the DPP was supposed to be further investigated for textiles and electronics. On this slide and on the next one, I brought some quotes from the individual documents in order to highlight some characteristics. The digital product passport is supposed to deliver some specific type of information which focus on circularity. However, the concrete type of information is not fixed yet. The Green Deal, for instance, speaks about information on a product's origin, composition, repair and dismantling possibilities, and end-of-life handling, while the Council more concretely highlights information on critical raw materials and recycled content. Information are supposed to be also compiled based on existing legislation and in existing databases. And next, the digital product passport will be used to disclose product information to relevant market actors. Activities on the German side also focus on, roughly sketching types of information, but they also link the concept of the digital product passport to the concept of the digital twin, which is a virtual representation of a product. It also focuses on actors, hoping that the DPP will support mandatory reporting for manufacturers and to create transparency for consumers. A database is considered to be central or a key element or a key infrastructure for the digital product passport. And the test and transition phase is found to be important to turn the concept into reality. Okay, so what do we have so far? The DPP will include product information, and electronics belong to the product group which are more concretely scrutinized at the moment. The concept of the DPP is linked to the concept of the digital twin. So a TV in this example would get a virtual representation through the digital product passport. The DPP might make use of a database which information are delivered to. It may affect all stakeholders in a value chain, and it may require suppliers and manufacturers to deliver information. It may help consumers to make more sustainable choices, and it could serve professional repairers and recyclers or waste treatment operators to improve their business models. And market surveillance authorities could use the platform to check whether information delivered are compliant with existing legislation. Well, on this slide, I would like to show how information flows are currently regulated under the eco-design, energy labeling, and WEEE legislation. Eco-design sets energy and increasingly circularity requirements, and if met, manufacturers can put a CE marking on their products. Moreover, eco-design requires manufacturers of electronic products to provide information to professional repairers and to waste treatment facilities. Energy labeling regulation requires the disclosure of the energy label and of technical information through product data sheets. And the label is important for retail and for consumers to make more sustainable and energy efficient product choices. Mostly energy-related information needs to be fed into the EPREL database by manufacturers. Consumers can access selected information from EPREL, and market surveillance has full access to all data delivered. Last but not least, WEEE requests manufacturers to deliver information on components and materials, as well as the location of dangerous substances and mixtures to treatment facilities. So here we see the two systems in a comparative perspective. If the DPP system, as illustrated before, becomes reality, focusing on circularity, we may see some information flows vanishing in the existing regimes. For instance, the information transfer from manufacturers to repair and waste treatment facilities. So one of the questions would be, do we need a second comprehensive data compilation system, which focuses on circularity and would resemble the system on the left-hand side, the DPP system? Or could we make use of EPREL as a, well, comprehensive database focusing on both energy efficiency and circularity? Before coming to my last slide, some words on EPREL. EPREL is an online database in which manufacturers feed relevant energy-related product information. It has a conformity area for confidential information, which you can see on the left-hand side, and a public database, which is accessible for everyone. Information provided by manufacturers are processed automatically so that the public can only access those information they are authorized to access. And well, given that the digital product passport may also require information that will either be irrelevant to some actors or confidential, actor-specific information access can be seen as one of EPREL's huge advantages. Still, there are some existing hurdles. For instance, EPREL itself has challenges, as most of the information delivered are public information. So at the moment, there is in fact no real need for a confidential area. Access rights need to be further refined, for instance, for repair professionals and waste treatment facilities, which at the moment do not or have no use for EPREL. Apart from that, the concept of the DPP is only evolving. So information types are just unknown. So before focusing on the database, we need more information on the DPP, and then compare EPREL with alternatives. As stated before, some also consider the REACH database for chemicals an interesting case for advancing the digital product passport. So what's next? We need a more concrete design of the DPP for different products, which is also enforceable. An EU-wide assessment is necessary to identify stakeholder needs comprehensively, including suppliers to waste treatment facilities and so on. A comparison or a SWOT analysis of existing databases could be helpful in order to check whether the DPP system or a potential DPP system could be aligned with the existing systems, data management systems. And the topic which we have not covered today is about information disclosure, and important questions are how would a DPP system disclose or even label information, and how would disclosed circularity information interact with energy efficiency information? Would an additional label disclosing circularity information be rather helpful and thus complement the energy label, or would it rather distract or overburden customers? So obviously, that's not a complete list of next steps, but now I would like to stop here and want to thank you for your attention. Here are my contact details, so if you have any questions or would like to carry out any further research on the digital product passport, please feel free to contact me. And thank you very much.
Thank you, Thomas, for this interesting presentation. So I think it's pretty exciting, this perspective to have this digital product passport. So what year do you think could it be realized the earliest? Do you have a prediction?
It's hard to say, actually. I hope everyone can hear me. There are plans to install a product passport for batteries in 2026. So there is some time left to discuss and to do research on all the relevant aspects I touched upon. But there are also, as I stated before, some pilots already initiated on the German side. I'm not aware of any projects on the EU level, but I guess there are also plans to do pilots on relevant product groups.
Well, you know what people want to know is if your baby arrived. And we maybe we can have other questions in the end, but that could be a short one to answer.
It hasn't arrived yet, but if I will run out of the screen, I will not get a coffee or so.
So let's actually try to squeeze this one in by Tina Fawcett. I am new to the concept of digital product passports. Is this aligned to life cycle analysis of products? LCAs are known to be complex to assemble and change with changing supply chains. Would DPP suffer from this too?
I haven't got the last words. Whether the DPP suffered from what?
From changing delivery chains. No, this is, I think I'm at the wrong comment here.
Regarding the LCA, I guess that there is an interest to include such information in the DPP, but as stated before, it's quite well unspecific yet what exact information types will be entered into what type of system. But I could imagine that LCA would at least be of interest to analyze for potential application in a DPP.
Okay, so let's hope you can stick around for 1 more hour and we can come back in the end, maybe. But now, thank you, Thomas, and we'll jump right to the next presentation by Hans-Paul Siderius. And Hans-Paul is an energy efficiency expert at the Netherlands Enterprise Agency, and he represents the Netherlands in the Eco-Design Committee, the Energy Label Expert Group, and he is a vice chair of the International Energy Agency's Technology Collaboration Platform 4E, Energy Efficient End-Use Equipment. And he will talk about work that they are doing in the 4E Systems Policy Working Group. So let's hear this interesting presentation.
Good afternoon. My name is Hans-Paul Siderius from the Netherlands Enterprise Agency, and I will present the paper Transforming Product Efficiency Policy into System Efficiency Policy. In the next 15 minutes, I will show you what the challenges are to regulate energy-using systems and provide suggestions to overcome these challenges. But first of all, I would like to introduce to you my co-authors, which are Roland Brüninger from the Swiss Federal Office of Energy and Adriana Diaz from the Eco-Design Company in Austria. Why are systems more difficult to regulate? Or why would a policymaker bother to regulate systems? The short answer is to realize larger energy savings. Although data is scarce and indicative, savings range from 15 to 20 to 50%. But system seems difficult to regulate. In this presentation, I show why. I will discuss these challenges and propose a classification of systems and present 2 examples and approaches to regulate systems. Finally, I give some recommendations for further investigations into this subject. What is a system? The general definition of a system can be summarized as an entity made of several parts. And it provides 2 perspectives, the one of the parts and the perspective of the whole, the functionality of the system, including the interaction between the parts and the interaction with its environment, as you can see on the figure here on the slide. The general definition also fits the products that are currently in scope of efficiency regulations, the products that are produced in a factory, assembled in an industrial process. A more specific definition for system efficiency policy has as essential and distinctive character that at least some of the parts are assembled on location before the system can function. And so the definition that we will work with in this paper is a functional unit that consists of 2 or more physical parts that need to be assembled at the location where the system is used. Much of the confusion between products and systems stems from the fact that both have to be installed, connected to another system, for instance the electricity grid or a piping or duct system for water or air. So what are sometimes called installed products are products that need installation by a professional. In the consumer sphere, these are commonly hot water, heating, ventilation, or air conditioning products. And on this slide, I will show you the difference between assembly and installation. The assembly of a system is putting together the parts that make the system a functional unit. And after that, the system needs to be installed. That is, to be connected to electricity or other systems, and have its output connected, for instance, to a piping system. A product has only to be installed. The assembly of a product is already done in a factory. Although this distinction is clear in theory, there are some gray areas, and we come to that in a minute. Products and systems. There are some gray areas between products and systems. Although the definition in theory is clear, there are some situations where both a product and a system can occur. Look at the examples on the slide. A domestic refrigerator is clear, it's a product, it has many parts, but these are not assembled in the home, but by the manufacturer. A walk-in cooler freezer, on the other hand, is assembled on location to match the geometry and conditions of the location. Some of the parts are assembled in a factory, but in order to function, the system in this case has to be assembled on location. The third example is a fan that may be sold assembled as a product, or as a fan, motor and variable speed drive in separate parts for assembly on location, and then it would be a system. The split air conditioner is also sold as a product, which is then professionally installed on the premises, and where you could say, well, is this installation or is it assembly? Certainly, if there are more parts that need to be put together. There are many possible types of systems, and to structure these and guide regulation of systems, we proposed a classification of systems based on 3 attributes. First, the impact of assembly on energy consumption or performance. Second, the number of parts, and finally the percentage of identical parts. Reducing the range of the values for the attribute and taking into account the relation between the attributes, we arrive at 5 classes numbered 1 to 5. And in the paper you will find more explanation about the relations between the attributes and how we reduce the range of values. And the complexity regarding these classes increases from 1 to 5. So 1 are the more simple systems and 5 the complex. And on the next slide you will find 2 examples. The first one is the water pump unit, an eco-design regulation that is proposed to follow up the current regulation for the hydraulic part of water pumps. And the water pump unit is an example of good that can be placed on the market as a product or as parts of a system, which are then to be assembled on location. It is a class 1 system. The impact of assembly on the efficiency or performance is small to medium, and the number of parts is small. 3. The variable speed drive, the motor and the pump. The main challenge is the verification and enforcement when the parts of the water pump unit are placed on the market separately and the unit itself is assembled on location. How, for instance, can a market surveillance authority know where a product is assembled, and then do they have the right to access that location and check the system? The second example is the walk-in cooler freezer that is regulated in the US. This is a class 4 system. The impact of assembly on the efficiency is large and the number of parts is small. Panels, doors and refrigeration unit. The enforcement and verification is mainly done on the parts, which have to be tested, certified and registered. DOE can also check test systems. The examples already touched upon some of the challenges in regulating systems. On this slide I present an overview of the challenges in general. First, the scope. as we have already seen, there can be a challenge in covering both the product and the system variant. You don't want a regulation that would only cover the product and leaving the system out of scope, because that can be a loophole. There are new addressees of the regulation, for instance, system integrators, that you will not find for products. Then the metrics and requirements, they have to deal with a large variety of locations and usage patterns. Verification and test methods were mentioned. Can there be testing on location? Are the results reproducible? And regulatory powers may be limited, related to the scope, territorial jurisdiction, or powers of market surveillance authorities. Now, what are the approaches in assessing systems? Because assessing the efficiency and performance of systems is at the heart of regulating energy efficiency. This slide provides an overview of the approaches. The black box approach is to test the system like a product. In the modular approach, the parts of the system are tested and the results are combined through a formula, for instance. Then the third approach is procedural, a quality management approach. The assembly and installation and possibly sizing must follow a certain procedure that then guarantees a good efficiency and performance. And the statistical approach is a monitoring approach where the measurement of energy consumption and performance is done when the system is in use. Note that this approach is currently out of scope of most or all regulatory schemes. However, current schemes may require that the product or system has monitoring features. And then modeling as finally approach, the mathematical model of parts of the system or a scale model. In this slide, it's summarized how the two system classes of the example shown earlier map on the main elements of energy efficiency measures. That are the scope and addressees, the efficiency metrics and requirements, and the verification and test methods. And you will find the mapping for the other system classes in the table in the paper. In this presentation, I gave you an overview of the challenges of regulating systems and proposed a classification of systems that can guide regulatory solutions. Also, I presented some approaches to assess systems and mapped these to the main parts of these regulatory aspects. I hope you agree that the system is not something magical that escapes energy efficiency policy, but it can be regulated with useful policy and approaches. However, what was presented was only mainly a theoretical outline, which of course has to be applied, tried out in practice. The example show that this already is being done or proposed in several jurisdictions, but certainly more experience would be welcome. And I end with a couple of recommendations for this. First of all, as I mentioned in the beginning, the savings potential is the data on that is scarce, and therefore it could help to provide a better estimate of the savings potential. When the assembly has a large impact on the efficiency or the performance of a system, include the assembler as addressee and focus on the quality of the assembly, and include a regulatory option to regulate standardization of the assembly. For quality control, look at approaches used in buildings, and finally use modeling in the verification of systems if the variety in conditions and systems is large. Include then the model in the regulation and indicate how third-party calculations or simulations can be verified. Thank you for your attention, and I'm happy to answer any questions.
Thanks for this presentation. So Hans-Paul, I think you're primarily focused on mandatory requirements for systems. How do you see it in the with voluntary policies? Is there maybe a bigger chance, or is it easier to do system requirements there? And in which systems do you see a big potential? Like, where are your priorities in what systems?
In voluntary systems, I think it is indeed easier because in general, for voluntary measures, say the market surveillance is either not there or more simpler, because voluntary schemes there, the manufacturer wants to be part of that scheme, and therefore has an interest in providing the information that is needed. And as you saw from the presentation, for instance, for models or also for certification of parts, information provided by the manufacturer is very important. What would be interesting systems to regulate? Yeah, it depends a bit on where you come from. I think what the EU now is doing with the water pumps, but that's a mandatory approach, is a good thing to start. If you would like to experiment more with voluntary approaches, then you could use, for instance, more complex systems. There are some developments regarding building automation control systems already, and yeah, that could be used for voluntary measures.
Thank you. Let's see. How do you see the risk of adding measurement tolerances when many components are included in a system?
Yes, that would be the case if indeed you measure the individual parts and then put them together. Yeah, it's not so different from the practice currently in eco-design and energy labeling, where, for instance, for an energy efficiency index or another metric, you also may have several measurements and result of that measurements that then need to be brought together to the final result. And I think it's a matter of checking and keeping control of the tolerances of the individual measurements. And that can, for instance, be done by, say, moving the risk of being out of tolerance to the manufacturer.
Mm-hmm. So Niels Borg has here a question, a compliment. Great systematic organization of the topic, thanks. And the question, many manufacturers that deliver systems claim that components should not be regulated since it is the system that matters. Is there a way to quantify the importance of catching component regulation as a safety measure?
Yes, thanks for the question, Niels. In the paper, there is a short paragraph on this. In short, components are still important, certainly if they can also be used outside the systems that are regulated. An example, well-known example, is electric motors, where manufacturers have argued that certain motors should no longer be regulated because the systems or the products in which they were used are already regulated. However, it's very difficult to see when a motor is manufactured and placed on the market that it's used in a product or a system that is already regulated or not. And also there is, as I've shown, there is the situation where you say regulate the system by regulating the components. And then also this is important. So I think it needs to be a case-by-case consideration, but it's certainly not an automatic reflex that you need not regulate components when you have regulated the system.
Thank you. I hope we can come back to some questions in the end. It's now time, thank you, Hans-Paul, and it's now time to go to the next presentation already. So we have Michael Scholland speaking next, and Michael is Senior Advisor at CLASP Europe and based in the UK. And he has a plan to phase out fluorescent lighting all over the world. And he wants to do this not via minimum energy performance standards, but via environmental regulations that restrict mercury. So let's hear how that goes.
Thank you, Eva. Actually, I don't have a preference. Either mechanism is fine with me, just as long as we get the outcome. But yeah, this paper is on the environmental piece. So welcome everyone, and thank you very much for coming. I'm the black sheep of the panel. I'm the one doing it live. I didn't get it recorded in time. So I will try and be tight to the 15 minutes. My co-author, Peter Bennick, is on the line with us, and he will be elevated to presenter. So he will also be able to answer questions in the Q&A session when I'm done with the slides. So what are we talking, whoops. What are we talking about today? We're going to be discussing fluorescent lighting as a product. Now, you're all familiar with it. You probably have it in your home and your offices. It's been a dominant light source for over 50 years. It was actually invented in the 1930s. And around the year 2015, it was around 70% of the artificial lumens produced by light sources. So it really has been a workhorse of the industry, providing light in our homes, buildings, and living spaces. All fluorescent lamps contain mercury. It's a necessary part of the light production process. And as you probably know, mercury is a very dangerous neurotoxin for humans and the environment. These products, the ones pictured here, the tubes and CFLs, are regulated under the Ross Directive, which is what I'm focusing on primarily today. Also eco-design and the waste of electrical and electronic equipment, the WEEE Directive. So let's just start with the Ross Directive first. Ross was passed in 2003 and then took effect 2006 and had a major revision in 2011 when the requirements on fluorescent lighting products were updated, made more stringent. Ross is covering 10 different substances, one of which is mercury. And for fluorescent lighting, the way Ross works is it sets a maximum amount, milligrams, per lamp or per bulb. So manufacturers placing on the market have to make sure their products are at or below that maximum quantity of mercury. And Ross is a CE marking directive, meaning all the products have to have this limit. They must comply with this regulation. Eco-design, it almost seems comical to present this to panel 9. I'm sure all of you on the call know about it already, but because it's a paper, I'll go through the steps here. So eco-design was passed in 2005, was recast in 2009, and it establishes a public participative process for developing quality and performance regulations of products. Lighting products are covered, including fluorescent lamps, and those were regulated under a series of regulations starting in 2009. All the actual citations are in the paper, but basically it's been regulated for a while, for over 10 years. However, the focus of the Eco-Design Directive has been on the energy efficiency of fluorescent lighting products, not looking necessarily at the toxicity aspects, partly because it's already covered under Ross, but anyway, that's where the focus has been. But there have also been quality requirements such as lifetime and time to brightness and things like that that are in the regulations. Eco-design, as you all know, is also a CE marking directive, meaning suppliers must comply with that. So we did a little comparison in the paper between the two directives just to kind of identify some of the differences between them. So Ross is a delegated act. The Commission, DG Environment, has the authority to carry out the regulation. They have expert consultants who work for them. Occo Institute is one of them. And I talk about an Occo Institute study in a minute. They have member states participate, but as expert advisors, not as decision makers. So there isn't like a member state vote that takes place on amendments to Ross. There is no public participation in this process. So DG Environment can invite experts to come in, people from industry, people from NGOs, but there isn't a consultation forum equivalent on the Ross side. Letters and information that have been submitted by member states to the Commission are protected under confidentiality. If you want to get access to those, you have to go through a Freedom of Information request, and it takes anywhere from 30 to 40 days to get a response. So there is a barrier to information in Ross, or in the Ross process, in the decision-making process. And there are no mandatory deadlines for DG Environment when they have to update the exemptions or the allowances that are in Ross. The guidance is that it should be every 5 years. However, as I mentioned earlier, Ross was recast in 2011. So the revisions that were expected in 2016 have actually still not been revised for lighting. So we're still using the ones that were set back in the 2011 version today. And it's also important, Ross actually drives decisions whether products should be exempted, not on the basis of least life cycle cost, like we have on eco-design. It's driven by toxicity. And if there are products that are alternatives that don't contain the regulated products, such as mercury. So if alternatives exist, cost effectiveness is not actually part of the statute, the law, the statute. The DG Environment can make a decision to phase out just on the basis of alternatives that don't contain the hazardous substance. So it's actually a very powerful directive. On the eco-design side, as you all know, it follows comitology. There are several commission DGs that can administer and run a proceeding for a specific product. Decisions are made by the member states in the regulatory committee. So there is a high level of, well, the decision actually, the final decision rests with the member states. There are expert consultants, of course, who also contribute with preparatory studies, review studies, and impact assessments and so on, who are feeding into the whole process. And of course, I highlight here that it's highly transparent and participative. The consultation forum is a great venue that includes member states, industry, NGOs, civil society. There's a lot of discussion and collective thought that goes into the policies on eco-design. Decisions on eco-design are driven by several factors, and one of them is, of course, as I mentioned, the least life cycle cost. So I apologize for the very small print on this table, but I just wanted to reflect what was in the paper, and I'll talk through it briefly. So this is a timeline from 2016 to today. Back in June, so where we get now 2021, so we're going back 5 years, the Occo Institute identified mercury-free LED alternatives to certain common fluorescent lamps. And they recommended in that report that some fluorescent lamps could be phased out under Ross starting in 2017 and 2018. The DG Environment, obviously this was an interesting finding. They felt it was necessary to launch a socioeconomic impact assessment to assess the impact of what that would have, because that there is some language in Ross that indicates socio-impact assessments, socioeconomic impacts should be taken into account. Drafts were prepared over interim years, and in the process of that, Peter Bennick, my co-author, was approached by the Swedish Environment Agency, who are sitting as one of the expert representatives in Ross, and they asked for Peter's opinion on the findings. Peter brought it to my attention, and we realized, oh my goodness, this data is a little out of date. The LED products that they were considering in 2019 were based on 2013 to 2015 models. And there's reasons for that I won't go into, but Peter and I then started preparing a series of studies. And so there are 3 studies we came out with over the next 12 months. They're all linked in the paper and you can download them. And these were essentially intended to establish an evidence base to provide the member states advising the commission and also the commission itself in its decision on fluorescent lighting. As we stand today, we are expecting, I actually, when we started this paper, we had hoped to be telling you that here is the commission's draft position, and we wanted to kind of identify and discuss it in the paper. However, for various reasons, the commission has not yet published their draft position. We are anxiously awaiting it to appear in the Have Your Say webpage. I checked last night and it's not there yet. So could be any day. I'm told anytime in the next few weeks. On the eco-design side, just to show you what was happening in parallel with this, there was obviously a review study for the single regulation that was conducted. DG Energy published their first draft in December 2019. And interestingly enough, applying the principles of the eco-design directive to the products in question, VHK's recommendation in that first draft was to phase out fluorescent lamps in September of last year already. Then of course there was some pressure that was put on the commission and revisions were made, and the proposal that went into the regulatory committee in the decision in December 2018 was for September 2021. So it was a 1-year delay on the phase out of linear fluorescent. And what came out of the regulatory committee was a further 2-year delay. So we're sitting with T8s not being phased out until September 2023, when the purest application of eco-design was for 3 years before that. So this is a sentence from the paper that I really like, and I made it a whole slide. So Ross essentially offers the commission an opportunity to expand the scope of coverage of lighting products that were excluded under eco-design, and to accelerate their phase out relative to the business as usual case due to toxicity rather than least life cycle cost or some other factor. And so this is, of course, one of the key questions that we get asked. Are there mercury-free alternatives? And the answer is a resounding yes. There are literally tens of thousands of mercury-free LED retrofits available. Different diameters, lengths, ballast types. That's a compatibility issue with magnetic or high-frequency electronic ballast, different color temperatures, levels of light output. And what you see pictured, oh, sorry, I'll just finish this. There's also a question like, do we need to change our luminaires? Do we have to rewire and so on, or is it easy to do? And it is actually quite simple. And we have some quotes here from industry's websites that it's a fit and forget, it's a plug and play, it's straight out of the box. You can keep your existing fixtures, just change the bulb. And you can see an image there on the right-hand side. Peter and I put together a database of manufacturers' compatibility tables. And you can download this. There's a link there in the slides. It's a database that's also in the paper. But we found that 91 to 93% of the existing ballasts in stock across Europe today can accept a direct replacement LED tube now. And yeah, and save energy from there. Okay, I'm running out of time. This slide, I wanted to talk about what would happen if the commission took the step. There are very short paybacks for T8. It's 4 to 10 months, and the lifetime is 2 to 3 times longer. For T5, the payback is a little longer. It's just over a year, 1.1 to 1.4 years. products will last for 16 years when installed. That's a 50,000 hour life compared to 24 for T5. CFL pin base is also a little bit longer, but again, you get the same benefits, positive payback. And the ACO Institute and VHK collaborated on a study published in July. There's a link to it here in the footnote, and you can see the benefits across Europe for taking this step. It will save 5.4 metric tons of mercury from the market, 30 billion euros net savings. That's including bulbs, that's including labor for installations, for replacing some luminaires, and of course, electricity savings. 310 terawatt hours of electricity, the equivalent of 7 power stations over 15 years. It's very significant. Yeah, I've really run out of time. There are problems with recovery of fluorescent lamps, which we highlight in the paper. Essentially, there are claims, you may have seen, that 100% of lamps are recovered, but that's a problem with the definition of recycled in the WE directive. They're calculating the percentage of what is delivered to recycling centers, and that's actually not what is placed on the market. We found it's actually, using a series of papers and reports from various member states, it's around 50 to 83% of fluorescent lamps end up not being disposed of correctly. So it's actually a very bad situation for Europe. And there's also mercury that's emitted from coal-fired power stations because of their inefficiency. So scaling up to the global market, there is this convention called the Minamata Convention on Mercury. It was launched in 2013. 131 countries are parties to this, including 25 of the 27 EU member states. And it includes exemptions for fluorescent lamps, where that was appropriate in 2013. Now, with the advent and the growth of the LED market, Peter and I don't feel that's justified anymore. And so we're supporting the concept of phasing out fluorescent lamps under Minamata by 2025. There is a conference of the parties this year that kicks off in November, just online. The in-person negotiation where the amendments will be discussed will be around this time, 2022. This time next year, a year from now. There was an amendment submitted by a group of African nations, 36 countries, calling for the phase out of CFLs by the end of 2024 and linear fluorescent lamps by the end of 2025. And just to say that, what are the benefits from this? Well, last year, 3.3 billion fluorescent lamps were sold. We're talking 16 to 33 tons of mercury, depending on how much there was, based on 3 to 5 milligrams per lamp, which are placed on the global markets. There's still lots of mercury that's coming out. And if these were to be phased out, if the African Amendment went through, we calculate between 2025 and 2050, a savings of 232 metric tons of mercury will be avoided from the lamps and the power stations, and 3.5 gigatons of CO2 savings because of LEDs being 50% more efficient than fluorescent. There is a Clean Lighting Coalition, a new campaign that's been launched to support that. You can click on the link there to learn more. So the conclusion, Eva, yes.
Can you sum this up in 10 seconds?
10 seconds. So eco-design removed many fluorescent lamps, but not all. Ross Directive is hopefully going to clean up what was left behind. Most fluorescent lamps are not disposed of properly in the EU. The best way to solve this problem is to stop selling them and to transition towards LED. It is cost effective to do so. There's a high level of compatibility with the existing stock of luminaires. And the Ross exemption has been delayed so far, but we hope the Commission will move forward with it soon. And then Minamata allows you to scale up these benefits to Europe, to the globe. It's time to say farewell to fluorescent. Thank you.
Thank you. So I think we have to put the questions to the end of this session because it is already time for the fourth presentation.
Sorry.
Okay, but you stay here and Peter can then also come in the end. And we have some questions here that we can discuss after. Thank you, Michael. So next, let's hear the presentation by Nashwa Susali. And Nashwa is a researcher at Fraunhofer Institute for Systems and Innovation Research in Germany. And she will talk about network-connected household appliances and how high their electricity consumption might be, including the energy required by the data centers and for the data transfer.
Hello everyone, I will be talking about the electricity consumption of network-connected devices in the residential sector in Germany. I study in collaboration with the Compatibility Institute for Systems and Innovations Research in Karlsruhe. I'll start the presentation with some introduction, the research questions, the methodology, results and discussions, and finally the limitation and future work. So the study is motivated by the information provided by the International Energy Agency for Germany, the year 2018, where the residential electricity consumption amounted to 25% of the overall final consumption by sector. And so although this figure shows stagnant consumption, the rapid transformation of digitalization has increased the use of network-connected devices and thus also increased data traffic between devices. And a reported figure from another report suggests an exponential increase in the global transfer of data with this rise in internet traffic. So to have a general overview, network-connected devices are sometimes referred to as Internet of Things and smart devices, and they reflect the ability of a device to communicate between one another. And so its communication results in increasing amounts of data that must be generated and processed. And that's where data centers are built. It's to meet up this demand because these processes require power and data storage capacity. So the question is, what is the upstream energy related to network-connected devices in the residential sector? And so in this study, upstream energy refers to the combined energy that data centers and wide area network involved in the transfer of data between connected devices consume. And so the second question is how much of electricity consumption in the residential sector is contributed by the connection of smart devices. In these, the following study uses a scenario analysis, and it's simulated to query the effects of electricity consumption through the changing policy, user behavior, and developments of the improvement of data center efficiency. The Assimilation model used in this study follows a bottom-up approach and is extended from the existing forecast residential model by Fraunhofer eceee, which is used to support strategic policy decisions. So it is a technical economic model which is able to analyze the technical and economic performance of a process and allows for comparative analysis. What this also means is that the model is also able to have an extensive technological detail that have different sectoral levels. And this is the structure of the forecast residential model with three different sectoral levels of end-use technology and efficiency classes. So the extension is that smart devices are either introduced on the technology level or they are introduced as an entirely new end-use. The simulation period for the study is between 2015 and 2035, and it uses a bias growth model to determine stock transformation, where it considers the path between new technology, entering the market, and replacement of the old technology, and it's therefore influenced by innovation, limitation, and the market potential The BAS model tells us exactly how much stock of appliance should be in a particular year, but to determine end user purchase and market share of an end use, the utility function and market share functions are computed. So the utility function simulates customer purchases based on cost, and here based on the net present value, applied subsidies, average maintenance and operation cost, and is then divided by the number of available alternatives. The market share uses a logic approach because in reality purchases are not only based on monetary value, but can be very much influenced by personal preferences. And these preferences are represented by the heterogeneity of the market. And To have a better overview of this, for example, we have an expensive television and a cheap television, and we know that not everyone is going to purchase the cheaper version because that's just not how the market works. And therefore, this lambda catches exactly this influence of choice by customers. The methodology to calculate upstream energy is presented here. So the upstream energy is the data flow between data centers and residential data demand, but the boundary of the network process includes the on-site networking equipment, such as the set-top boxes, wireless router, and the access networks such as a DSL or fiber networks. And in this study, only DSL connection is used due to its dominance in Germany. So the calculation follows a data flow which contributes to the demand in electricity. And from this equation here, we can separate the different connections. First, between the user devices to the on-site networking equipment, which tells us how much data is demanded. And this is given in gigabytes. And second is the energy intensity of the access network, which measures the efficiency of data transmission through the internet. And this is given in kilowatt hours per gigabyte. And third is the data center efficiency or power usage effectiveness, which provides us the information as to how effective the data center operates in respect to the power it requires to maintain its IT equipment. And in this study, it's given as a global parameter. So I would like to have a little focus on the energy intensity because it's based on a study by Adesar and measures the efficiency of internet data transmission. Because it will be a huge topic of discussion. So the background of energy intensity is first the definition, of course, it's the measure of efficiency of data transmission through internet over time. And according to Adesar, et al., it is decreased by half every 2 years in developed countries. So the initial study produced estimate between 2000 and 2015, and in this study, the remaining years were extrapolated. And this would, this graph on the left is how it would look like after being extrapolated. So the methodology for the electricity consumption is first to determine the different modes of operation. And these are the different modes of operation addressed in this study, which is the operation on mode, standby mode, and then active network standby mode. An easier method to identify these, how this is used, is to look into an example. And again, you have the television, you have a conventional, and you have a smart television. And so these two have a similar primary function in which they display content through broadcaster channels. But what they have in different is the secondary function where conventional TV does not have. And a smart television has a secondary function where it's connected to the internet to display online media. And so in this case, the electricity consumption in a conventional television is divided only between operation and standby mode, whereas the smart television has all the 4 different modes. And this concept applies to all NUs where the primary and secondary function is distinguished first in order to answer the research question. To determine the influence of policy and user behavior in efficient data centers and electricity consumption, scenario analysis was computed. And with every scenario analysis, we start first with the reference case, which is in this study called as business as usual, and it considers all minimum policy requirements. And then we have a scenario where the best available technology is selected, and this means that only highly efficient devices enter the market. To address user behavior, smart device purchases were investigated. The target share of 50% or more smart device purchases were set to meet by 2035. And another scenario addressing user behavior is through the increase in data transmission, where a 30% additional year-on-year increase in comparison to the business as usual was simulated. The data to investigate the data center efficiency, the power usage effectiveness of 1.12 by 2035 is set in in this scenario. And the reason why 1.12 is set is because of the lowest recorded power usage effectiveness in 2018 by Google. For a little context, the data center efficiency for the business as usual reaches 1.4 by the year 2035. Moving on to the results and discussion, all the answers are based on scenario analysis. So to answer the first research question, we first look into the electricity demand without the upstream energy. And immediately here in this figure, we see that the biggest reduction is from the best available technology, followed by increased smart device purchase scenarios. And this is because smart devices are commonly more efficient themselves. The remaining two scenarios have no effect on the electricity consumption, and therefore we look into the combined residential electricity and upstream energy demand against the business as usual scenario. We see some change in the data transmission scenario, but the data center scenario remains unchanged. And remember, according to the equation used in the study, the trend in upstream energy is dependent on volume of data transmission, energy intensity of access network, and the development of data center power usage effectiveness. But we see little to no difference in increasing the efficiency of data centers, and this raises an important discussion on the energy intensity of access networks with respect to the direct connection between data demand and energy consumption of data centers. And here is a summary of the results with the two decreasing demand by the businesses, best available technology and the increased purchase of smart devices, and the increase in demand in terms of data transmission in the upstream, in the combined residential and upstream energy demand, and no difference in the data center scenario. And looking deeper into upstream energy in the reference case, the study finds that there is a year-on-year decrease in upstream energy, although there's a year-on-year increase in data usage. And this is again due to the energy intensity value taken for the study. So we know that the upstream energy has a high influence from energy intensity. And but when we look a little closer into the figure 8 on the right here, we also notice that smartphones have a high share in data usage, and maybe it pops a little question, but it's a study by Ericsson expects this trend to actually grow due to video-rich applications and the adoption of immersive consumer services such as virtual reality and augmented reality. But due to the simplicity of the model, I cannot conclude here, but the limitation, but there is a limitation that needs to be addressed. And so before we move on to the final slide, look into the network connected energy demand to answer the second research question. And here we have all the different operation modes aside from the operating mode. And we can see that the electricity demand in red, which is represented by the network standby, is consistently higher than the normal standby mode. And this is actually reflective. This is reflective of the high amount of wide appliances with network standby mode. And finally, the study is only strengthened by addressing the limitations and its possible future work. So the model is limited by the simplicity of assuming only DSL connection throughout Germany, and fiber networks are slowly being rolled out. And this introduction to the model, the distinction actually allows to investigate what potential other access network may provide in terms of energy intensity. And of course, the limitation of the model is the simplicity of energy intensity, where considering a direct translation of data to demand it cannot be easily translated with just one unit. And so the future work should consider the complexity of energy intensity and needs to incorporate the different types of access network, the usage hours of a device being connected, the data transmission based on sources, and the distance between source of demand to its nearest data center. And this is where the power usage effectiveness of a data center is important instead of just a global parameter. And then what would be also additionally interesting is the addition of demand side management to further illustrate the electricity abatement caused by smart devices. And that is the end of my presentation, and thank you for listening.
Thanks for this presentation, Nashua. Maybe a comment on my computer, the sound was quite bad, but the recording will be posted on Woofa after, so maybe if somebody else had troubles understanding, you can also go back and look at the recording again, maybe with better sound. So Nashua, can you maybe tell me a little bit, because I don't really know connected devices so well, like what devices are we talking about? Are there ones that actually have higher energy consumption in total when they are connected compared to when they're just conventional, and which ones are the important ones?
That's a good question. And I'm sorry about the video. I'm not too sure what happened. Smart connected devices come in, they come in many devices. I think if you would know your Alexa or your tablets, they're all connected to the internet. So these are what's considered smart devices. There's also some things like smart refrigerators, for example. They monitor the temperature in your fridge, for example, or they have some fancy ones also have like cameras in the fridge department where they monitor what's missing in your fridge. Those are the kinds of smart devices available, let's say. So that's your common wide appliances are in this category of smart refrigerators or your smart ovens, where they regulate a lot of energy.
And so overall, you're pretty sure that they will lead to a reduction in energy consumption?
I think it's also because these smart devices are new devices that come into the market, so they already have a threshold of efficiency where they cannot go beyond a certain number, and that's why it's also contributing to the low demand in electricity in comparison to older versions of appliances. Yes.
Okay. So let's see if we have anything in the chat here. There's from Stefan Thomas. Did I see that correctly? He asks, networked standby is modeled to grow to 20 terawatt hours a year, so 20% of residential electricity demand, and eating up all savings from eco-design and labeling in other appliances.
And eating up all savings from eco-design and labeling. If the question is this 20% growth is actually replacing what is supposed to be saved, then I don't think so, because I think it's also because there is a growth in a particular device throughout the years, and it's not exactly taking up the demand. It's just that it's shifted from being maybe not under the conventional device, but into a network standby mode, so to speak. Mm-hmm.
Okay. So any more questions? I'm just waiting if one more question comes for Nashua in the chat. And otherwise, I would say we could also open again, and maybe all the speakers can join and turn on their cameras, and we can open again the discussion for everybody. Yeah, I think there's no more question coming now, right now for Nashua. So thank you again very much for the presentation. Okay. Thomas, I don't have WUFA open. Sorry, can you post or tell me? I got a message here from Thomas. But let's take up a question that came for Thomas Adesar, and it was Carsten Schischke. He asked, comment maybe more. The stakeholder needs assessment is crucial. There are so many high policy hopes what a digital product passport might deliver, that there is a risk that this project will become an endless endeavor. And so, Thomas, the question to you, what are your most important issues for this DPP?
Yeah, as Carsten already noted, I also agree that the needs assessment is very crucial, and we also carried out a stakeholder workshop with the German stakeholders, and we also got a discussion with the Federal Ministry of the Environment, and all said that such a needs assessment is really essential. And in this respect, I think it's also important to reflect upon what manufacturers can actually deliver. So the needs need to be matched with opportunities and restrictions in terms of technology, in terms of well, processes. There is a long way to go, and a lot can be done in this field. And yeah, that's also why I called everybody to reflect on the DPP. And if you want to carry out some research on that, I would be glad to. Well, if you drop me a line.
Eva, if I may add a short sentence to this, I fully subscribe the warning from Carsten that the endeavor may be endless, and I would also warn a bit for extensive consultations on stakeholders' needs, but because the issue is that you will get a kind of Christmas tree with all nice bells and whistles. And I've seen already comments from member states on the digital product passport and wishes that go in that direction. So I would prefer that the Commission and member states would start with something simple to prove that it can work, and then we can build upon that. And then we can start directly instead of spending years on assessments and building something that would be too complex from the beginning.
Mm-hmm. Thanks. And I just want to ask for clarification, this digital twin, is it for the unit or for all the units that are a model?
I guess it's rather seen for models actually, so not for the actual unit. But well, that also needs to be discussed whether, for instance, for batteries, that's rather something where, well, the unique battery or information for the unique battery is supposed to be delivered, or at least that's proposed by the Commission. Yeah, we'll have to see how this develops.
Thank you. So here is a question by Carsten Schischke for Michael. So are there any cases where fluorescent lamps cannot be replaced by LED?
Yeah, that's a very good question. Thank you, Carsten, for that. I've had 15 minutes to prepare my response. But it's funny, and I feel bad running over. Anyone who knows me knows when I get onto lighting, it's hard to get me to stop. So apologies for that. Yes, there are actually, I would say, no applications apart from certain safety lamps and the emergency lighting, and there's a very specific reason for that. So let me just first mention CFL pin-based. There are 19 different base types for CFL pin-based. There are currently 16 of those 19 already available on the market. And for those 3 that aren't, I contacted 3 Chinese manufacturers who said they could easily make it for me within 3 months. I just needed to place an order for 10,000 units. There is actually no technical barrier to producing all of the products in LED. The barrier is, in fact, volume and demand. So pin-based, no problem. Their LED lamps are 100% compatible with magnetic ballasts. So I don't know if can you guys see the video that we're running? So this is a magnetic ballast from the 1950s that was here in this room. It's 100% compatible with LED today. No problem there. The place where there are some compatibility issues and why Peter and I prepared that big table is electronic ballast, the high frequency ballast. There can be compatibility issues there, but we find 80 to 90% of them are covered. And when you look across the stock of Europe, that's how we arrived. You know, there's still 50% of the ballasts in Europe are magnetic. That's how we ended up with the 91 to 93% compatibility number. So just turning to emergency lighting, which is the one where there's an issue. The standards body that establishes the regulations around emergency lighting have not approved LED products to be used in those luminaires. So they can, because there isn't a lot of difference, right? It's a driver, it's a fluorescent tube. They can be used, but they're not allowed to be used by the standard. And if you're a building owner and you have to have certified products for your building in order to maintain your fire code regulations and your insurance policy, that's an issue for you. So what's been happening mostly in the UK is they've been simply taking out the fluorescent and putting in LED emergency lighting, which frankly is better because they're more efficient, so the lights last longer. Okay, so that's what I was going to say on that person. Oh, and one other thing I forgot to mention, Cibero Corporation, in the country where Hans Paul is speaking from now, in the Netherlands. I mentioned 80 to 90% compatibility. That's looking at the big 3. That's looking across Signify, Osram, and Sylvania. Cibero has proprietary technology that is 99% compatible with the ballasts of Europe, and you can learn about them. If people are interested, just contact me, and I'll send you a link to talk to them. But they have a product that is 99% compatible across Europe. Okay. Thanks, Eva. Should I jump to the next question from Thomas?
I think actually we have time for you to keep talking because
keep talking about lighting.
and also in the WOOF chat, people can also see what Peter Benich commented, so you can read that there. And Michael, so talk about what was the reasoning or the data used by the regulatory committee to reject the complete phase out.
Yeah, and this, I was actually just going to queue up the question and then turn to Hans Paul. So the regulatory committee is a Chatham House rules meeting, so it's confidential. I was not there. Peter was. Unfortunately, he's gone. Hans Paul was there, so he can maybe speak to this question directly. But one thing I will say is there is still fluorescent lamp manufacturing in Europe, in Poland and in Germany. We are still producing fluorescent tubes here. So perhaps that was a factor.
Yes, indeed, that you could say there were certain economic considerations that factored that in, and that is Peter, as you mentioned, or Michael, in eco-design is, say, oriented based on a life cycle cost, but also another impact approach, and not primarily the substances, because that is ROS and REACH. So that is indeed the background of keeping the T5 in and having a bit longer for the T8. But I guess we will see naturally that that these lamp types will disappear in the end. I guess even without firm bans in Europe. Worldwide, it might be different.
All right, thank you, everyone. On my screen already popped up that the next session is starting in 14 minutes. And this will be the closing session to the conference. It starts at 2:15. So yeah, I guess we'll all hop over to that session, and it's just left now to thank again to the speakers and to everybody listening and posting questions. And it was very interesting, and yes, enjoy the rest of the day. Thank you very much.
Thank you.